When I was a kid, I used to think space was the closest thing to nothing. No air, no sound, no people, just endless darkness with a few stars scattered across it. It looked empty, and honestly, I never questioned it. It's funny how the simplest ideas are sometimes the hardest to let go of. I will spend most of today calibrating the black star's deep space sensors. They're designed to detect incredibly weak electromagnetic signals from regions that, at first glance, appeared completely empty. Hours of staring at a screen full of numbers and wavelengths eventually led me to the same realization that changed physics forever. There is no such thing as empty space. That sentence sounds wrong the first time you hear it. Even now, after everything we've learned, my brain still wants to argue with it. I can look out the window and see darkness stretching for millions of kilometers in every direction, and yet physics insists that what I'm looking at isn't nothing. It's something far stranger. The question of whether nothing can exist is much older than the modern science. More than 2,000 years ago, the Greek philosopher Democritus imagined that everything in existence was made from tiny invisible particles he called atoms. Between those atoms, he believed there had to be empty space. Without emptiness, nothing could move. It was a remarkably bold idea for someone who had no microscope and experiments to prove it. But another philosopher disagreed. Aristotle argued that nature could never allow a vacuum to exist. He believed that empty space was impossible because if it ever appeared, nature would instantly fill it. His influence was so enormous that for nearly 2,000 years, much of the world accepted the idea that a true vacuum simply couldn't exist. Imagine believing something for 20 centuries only to discover it wasn't true. Everything began to change in the 17th century with an Italian physicist named Evangelista Torricelli. While studying how pumps move together, he realized there was a limit to how high water could be lifted. The explanation wasn't magic, it was atmospheric pressure. He filled a glass tube with mercury, turned it upside down, and watched a small empty region form at the top of the tube. That space contained almost no matter at all. For the first time, humans had created vacuum. It wasn't perfect by today's standards, but it proved that empty space could exist. A belief that had survived for centuries suddenly had a crack in it. Not long afterward, a German scientist named Otto von Guericke performed one of my favorite experiments in history of science. He built two large metal hemispheres, pressed them together, and pumped almost all the air out from inside. Then he attached teams of horses to each side and ordered them to pull in opposite directions. The horses strained with all their strength, but the hemispheres refused to separate. People watching thought the metal had somehow fused together. It hadn't. The real force holding them together was the weight of Earth's atmosphere pushing on the outside. The experiment revealed something profound. Air isn't just something we breathe. It has weight. It pushes on everything around us. Remove it and you begin to understand what a vacuum really is. At that point, scientists believed they had finally discovered empty space, but they were only at the beginning of the story, because over the next few centuries, every major breakthrough in physics made the vacuum seem less empty. One of the biggest surprises came from a man who had very little formal education. Michael Faraday was a university professor. He started his career as a bookbinder's apprentice. Every day he handled scientific books that belonged to other people. Instead of simply binding them, he read them. Those pages sparked a curiosity that eventually made him one of the greatest experimental physicists in history. Faraday spent years studying electricity and magnetism. At the time, scientists treated them as separate phenomena. But through countless experiments, he began to notice invisible patterns surrounding magnets and electric charges. He imagined these patterns as fields filling the space around every object. Many scientists didn't like the idea. How could empty space contain invisible structures? It sounded almost mystical. But Faraday trusted his experiments more than people's opinions. His work inspired another brilliant physicist, James Clerk Maxwell. Maxwell did something extraordinary. Using mathematics, he united electricity and magnetism into a single theory. Today we call it electromagnetism. His equations predicted something nobody has expected. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. Together, they sustain each other, traveling through space as a wave. That wave is light. Every ray of sunlight that reaches Earth, every color you see, every radio signal, every Wi-Fi connection, every message I've sent you, they're all electromagnetic waves. And here is the fascinating part. If light can travel through what we call empty space, then space can't simply be nothing. It must possess properties that allow these waves to exist and move. The vacuum was beginning to look less like an empty stage, and more like an active part of the universe itself. Then in the early 20th century, a quiet patent clerk from Switzerland completely changed the picture again. Albert Einstein asked a deceptively simple question. What if space and time aren't separate things? What if they've woven together into a single fabric? His theory of general relativity revealed something astonishing. Gravity isn't really a force pulling objects together. Instead, massive objects like stars and planets bend the fabric of space-time itself. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet bends beneath its weight. Now, roll a smaller marble across that sheet. The marble follows the curved surface, making it appear as though it's being pulled toward the bowling ball. Of course, space-time isn't literally a rubber sheet, and that analogy has its limits, but it gives us intuition for the idea. According to Einstein, planets orbit stars not because they're being dragged by invisible ropes, but because they're following the natural curves of space-time. Even light, which has no mass, changes direction when space-time is curved. We've actually observed this. During a solar eclipse in 1919, astronomer Arthur Eddington measured the apparent positions of stars near the Sun. Their light had bent exactly as Einstein predicted. It was one of the first major confirmations that gravity could bend light itself. Think about that, what that means. The emptiness between the Earth and the Sun isn't just empty distance. It's the very fabric that can stretch, bend, ripple, and shape the motions of galaxies. Today, we've even detected gravitational waves, tiny ripples in space-time itself, first predicted by Einstein and directly observed a century later by the LIGO collaboration. When two black holes collide billions of light years away, they send waves through space-time, and those waves pass through Earth's changing distances by less than the width of a proton. That's not science fiction, that's measurement. By this point, the old idea of empty space had almost disappeared. Faraday filled it with fields, Maxwell showed it could carry light, Einstein revealed that it could bend and ripple. Surely that had to be the end of surprises, but it wasn't. In fact, physics was about to discover that what we call empty space is far stranger than anyone had ever imagined. By the 1920s, physicists had become confident that they understood the universe. Matter was made of atoms. Space was a stage where everything happened. The laws of physics seemed elegant, predictable, and complete. Then quantum mechanics arrived and completely shattered that confidence. Some of the greatest minds in history, Werner Heisenberg, Erwin Schrödinger, Niels Bohr, Paul Dirac, and many others, began exploring a world so small that everyday intuition simply stopped working. One of the most influential ideas came from Werner Heisenberg. His uncertainty principle is often misunderstood. It doesn't say that our instruments are too weak to make perfect measurements. It says that nature itself has a built-in limit. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a flaw in our technology. It's a fundamental property of reality. For decades, physicists have tested this principle in countless experiments, and it had never been shown to be wrong when it is domain of applicability. At first, that sounds like an odd rule for tiny particles, but its consequences reach much further. If uncertainty is built into the universe, then complete stillness becomes impossible. Imagine trying to remove every bit of energy from an empty region of space. Intuitively, you might think you could eventually reach absolute nothing. Quantum physics says you can't. Even a perfect vacuum retains a minimum amount of energy, often called zero-point energy. At the quantum level, the fields that make up nature cannot be perfectly motionless. And this is where our understanding of reality changes again. Modern physics no longer describe the universe as being made primarily of tiny independent particles. Instead, according to quantum field theory, our best framework for describing elementary particles, the space is filled with quantum fields. There's an electron field, a photon field, a quark field, and many others. What we call a particle is an excitation, or disturbance, in one of these fields, somewhat like a ripple traveling across the surface of a pond. The pond exists even when no ripple is visible. Likewise, the fields exist even when no particles are detected. That means the vacuum isn't an empty container. It's the lowest energy state of these ever-present fields. You may have heard people say that virtual particles constantly pop in and out of existence. It's a useful way to build intuition, but it's not the full story. In quantum field theory, virtual particles are mathematical entities that appear in calculations describing interactions. They are not ordinary particles flying around that can be directly observed like electrons or photons. However, the quantum vacuum itself does produce measurable effects, and that's where things become truly remarkable. One of the most beautiful examples is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that if you place two perfectly conducting metal plates extremely close together in a vacuum, they should experience a tiny attractive force. No magnets, no glue, no electric charge pulling them together. Just the properties of the quantum vacuum. At first, this sounded almost unbelievable, but decades later, increasingly precise experiments measured the effect, confirming that the force exists and agrees closely with the predictions of quantum electrodynamics. Think about that for a moment. Something that appears to be empty can exert a measurable force. That still amazes me. Another famous discovery came from American physicist Willis Lamb. When scientists examined hydrogen atoms with extraordinary precision, they found that certain energy levels were in exactly where theory had originally predicted. The difference was incredibly small, but it was real. This became known as the Lamb shift. The best explanation came from quantum electrodynamics, developed by physicists such as Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. According to the theory, interactions with the quantum electromagnetic field subtly alter the energy levels of the atom. The vacuum itself influences matter. Pause for a second and appreciate how extraordinary that sentence is. The vacuum influences matter. Not because it's filled with invisible dust, not because there are hidden molecules floating around, but because the fabric of reality at the quantum level is fundamentally different from the pictures our senses suggest. Sometimes I wonder how many discoveries humanity would have missed if we had trusted only what our eyes could see. From here, looking out into the darkness, space still appears silent. Still, empty, but appearances have misled us before, and physics has taught us one lesson over and over again. The universe is under no obligation to look the way it truly is. After everything we've learned, you might think we've finally solved the mystery of empty space. The truth is, we've only made it stranger, because once physicists accepted that even a perfect vacuum possesses energy, another question appeared almost immediately. How much energy? At first, that sounds like a simple calculation, but it isn't. When physicists use quantum field theory to estimate the energy of the vacuum, the answer is unimaginably large. But when astronomers observe the expansion of the universe, the amount of vacuum energy that seems to influence cosmic expansion is incredibly small by comparison. The difference between theory and observation isn't just a little off, it's enormous. Depending on exactly how the calculations is performed, the disagreement can reach around 120 orders of magnitude. Many physicists describe this as one of the biggest mismatches between theory and experiment in all of science. It's known as the cosmological constant problem, and despite decades of research, no one has solved it. Then, in 1998, another surprise arrived. Two independent teams of astronomers were observing distant type 1a supernovae to measure how the universe expands. They expected gravity to be slowing that expansion over time. Instead, they discovered the opposite. The expansion of the universe is accelerating. Something is pushing the cosmos apart faster and faster. We don't know exactly what it is. Today, scientists call the unknown cause dark energy. Based on current observations, dark energy appears to make up roughly 70% of the total energy content of the universe. Think about that. Everything we've ever touched, every planet, every star, every galaxy, everything humanity has ever observed directly represents only a small fraction of what the universe contains. The rest remains one of the greatest mysteries ever encountered. Could dark energy be related to the energy of empty space? Maybe. Many physicists suspect there is a connection. Others think the answer may require entirely new physics. Right now, we simply don't know, and I think that's beautiful. Sometimes people imagine science as a collection of answers carved into stone, but that's never been true. Science is a conversation with reality. Every answer leads to better questions. Every discovery reveals another horizon. Democritus thought about atoms without ever seeing one. Torricelli proved that a vacuum couldn't exist. Faraday filled that vacuum with invisible fields. Maxwell showed that light itself traveled through it. Einstein revealed that space and time can bend. Heisenberg showed that certainty has limits. Feynman and many others uncovered the quantum world where even the vacuum leaves measurable fingerprints on reality. Generation after generation, each scientist believed they had opened the final door. Instead, they found another hallway. Sometimes I sit here aboard the Black Star, and looked through the observation window for a few quiet minutes before recording these logs. From this distance, the universe still looks almost peaceful. Dark, silent, empty. But now I know better. Between every pair of stars, beyond every galaxy, even in the darkest regions of the cosmos, the universe is still doing something. Fields are present. The space-time stretches and ripples. Quantum effects never completely disappear. And somewhere within all of that may lie the answers to one of the greatest mysteries we've ever asked. Maybe that's the real lesson. The opposite of knowledge isn't ignorance. It's certainty. The moment we become convinced that we've explained everything, the universe quietly reminds us how much we still have left to discover. If you ever look up at the night sky and find yourself staring into what seems like endless nothing, remember this. The darkness isn't the absence of reality. It's one of the richest and most mysterious parts of it. And perhaps one day, someone aboard another ship, somewhere unimaginably far from here, will finally discover why. Until then, I'll keep the sensors running. End of transmission.